Today's topic is DC node voltage analysis. And DC standing for direct current, which refers to a circuit in which all voltages and currents are constant in time. Later we'll talk about transient circuit analysis, where voltages and currents can be arbitrary functions of time. And then later we'll talk about AC, or alternating current circuits, in which voltages and currents are all sinusoidal functions of time. But today we're talking about DC circuits. So we will say a circuit is, quote, solved if we know all voltage drops and currents for the circuit components, or devices, or whatever, let's call them devices. Okay, so all voltage and current sources and resistors for our purposes. If we know the voltage drops and the currents, then we say that the circuit is solved. Knowing those voltages and currents, we can also get powers and any other electrical quantities of interest. So there are various ways to solve a circuit, and when we get to a relatively complicated circuit, often the only thing that will work is this node voltage analysis. It is the most general method. So we'll call this the node voltage method, is the most general technique we have. We can solve any circuit using this method. Now, for simpler circuits, we may use one of the methods we've already studied, and those might be simpler, right? But we can always use the node voltage method. And for that reason, virtually every computer analysis tool for circuit analysis uses the node voltage method. We're going to focus primarily on how to use it for pencil and paper analysis of circuits, in which we try to minimize the number of unknowns, so we keep our size of our equations down. And of course, on a computer, the computer doesn't have to worry about that. It can crank through a giant linear system with no problem. Okay, now this method, as the name node voltage implies, requires us to know what nodes, and especially what we're going to call essential nodes, are. Okay, so let's talk about that. What we're going to basically do is identify what are the so-called essential nodes. One of those we will choose to be a reference voltage, which will have a voltage of 0 relative to itself. And then the other essential nodes, at each one of those, we will have an unknown voltage, called the node voltage. And then at each node, we'll write an equation, Kirchhoff's current law, and we'll get n equations and n unknowns. So this is our idea. And those unknowns are the node voltages. So let's first talk about nodes. So a node is where two or more devices connect. And physically, for example, say these were two devices, and we have to connect them together. Maybe we would solder the wire leads together here. And so that would be a node. Node is where two or more devices connect. Now, if only two devices connect, we could call that a non-essential node, or a trivial node even. So let's say this is current I1 and this is current I2 in these two devices. By Kirchhoff's current law, right, if we make a little surface here, the current flowing in has to be equal to the current flowing out. And that just simply says that I1 is equal to I2, of course, which just says that two devices in series have the same current. Okay, so KCL is trivial, at a non-essential node where only 2 devices meet. If, however, 3 devices are connected at a node, like maybe in the following picture here, well, now this is an essential node. Three or more devices are connected. And in this case, let's say this is current I1, and this is current I2, and let's say this is current I3. Well, now at this node, KCL is not so trivial. Sum of the currents flowing in would be I1 plus I3 is equal to the sum of the currents flowing out, which is just I2. Okay, so that's not just simply that the 2 currents are equal, but it's actually an algebraic relationship. So this is a non-trivial equation, and that's why we focus on essential nodes. Now, when we talk about nodes, it's important to make a distinction between physical versus electrical connections. So for example, let's say we had a circuit and here was a resistor, and over here is another resistor, and then here we've got a resistor going up like so, and then maybe here is another resistor going down like so, and then here's a resistor going up, and then here's another resistor going down. So we look at that and we say, how many nodes are illustrated there? Well, there are, if we, for example, if these dots represented solder joints, we'd have 1, 2, 3, 4 physical connections. However, when we say a node, we mean electrical connections. And in that case, everything that's connected by a wire is part of the same node because it has the same voltage. So this is only one node, one electrical node. An example of this, common example, would be in household circuits. So say you have a room with 4 walls and there's an outlet on each wall. Almost always those 4 outlets would be connected to the same breaker, but they're physically separated. However, if you took the hot terminal of each of those outlets, those would all be part of the same node. And likewise, the hot terminal of the circuit breaker, even though they may be spatially very separated. So everything that's connected by wires is part of the same node. So be careful that you don't look at this and say, oh, here's one node, here's another node, here's a third and a fourth. These all have the same voltage. So there's no need for labeling each of them with a different voltage because the voltage is all the same. Okay, so that's an important distinction. Here's another thing that's important to remember. Voltage is relative, right? So what really matters is voltage drop. Between 2 points, from one point to another. And what that means is we can choose a node to be our voltage reference. So for example, in this case up here with this node, we might call this 0 volts. And we might attach this a ground symbol, right, which means that that's 0 volts. That's our voltage reference. So if we were to make voltage measurements in the circuit, we would put our black lead of our voltmeter here on the reference node. And of course, if we put the red lead on there also, we would measure 0 volts. And then if we move the red lead elsewhere into the circuit, we would then measure generally non-zero voltages. Okay. So We can always choose one node to be our voltage reference, and we'll talk about later about how we would make that choice to be most convenient for us to reduce our calculations as much as possible. Now consider the following circuit. Here we've got a current source driving two resistors in parallel. And let's say this source is 10 milliamps. And our resistors are 470 ohms and 330 ohms. And we want to find the voltage drop here across those parallel resistors, equivalent to the voltage drop across the current source. So we have techniques so far that we've talked about that we can use to solve this. We could take these two resistors and say they're in parallel, and we could do 470 parallel 330 is equal to 193.875 ohms. That's an exact expression. And then we would say, okay, that's the equivalent resistance of these two resistors, and then you've got 10 milliamps flowing in that, so V would be equal to 10 milliamps times 193.875 ohms, and that would be to three significant figures, 1.94 volts. All right, and if we wanted to do that solution for this circuit, that's how we would do it. But we're going to use this very simple circuit just to illustrate the node voltage method. Not that we would want to use it in a circuit this simple, most likely, but just to see that we do indeed get the same result and to get an idea of how, even with a simple circuit, we can apply the node voltage method. Let's redraw our circuit. And let's identify the essential nodes. Now let me first relabel here. The resistors. All right, the essential nodes. I'll put a little circle. This would be the surface over which you need to do Kirchhoff's current law. So there's where you have three or more devices electrically connected. Okay, so there are two essential nodes. But because voltage is relative, we can always choose one of these to be our reference. And so let's choose this one here to be our reference. So that automatically becomes 0 volts. So we'll just call it 0, node 0. And then the remaining nodes we will label with variables. Here we'll just have V1. If we had another essential node, that could be V2 and so on. Okay, so we have one unknown, V1. We should therefore get one equation and one unknown. Okay, so this is the basis of the node voltage method. We go to every essential node other than the reference, and we say, what is the sum of the currents flowing out of that node? Well, in this case, there would be three currents flowing out. And write those. So KCL at this node with voltage V1. It would be, let's call this, say IA, IB, and IC. Okay, so KVL would be IA plus IB plus IC is equal to 0 because we put these referenced positive all flowing out. The sum of all currents flowing out of through a closed surface is equal to 0. So now the key is to put in, using Ohm's law or other relationships, what these currents are and get an equation in terms of the unknown node voltages. Okay, so what's IA? Well, IA flowing to the left here, we can see there's 10 milliamps flowing up. So by Kirchhoff's current law, IA must be minus 10 milliamps because IA plus 10 milliamps is 0. So we would have minus 10 milli. We'll just leave off the units here. And then let's see, what's IB? Well, let's see, it's the current through a resistor that has a voltage drop V1 minus 0. So that's plus V1 minus 0 over the resistance, which is 330. Okay, so that's current IB. And then IC is V1 to 0 is the voltage drop through a resistor 470 ohms. So that'd be plus V1 minus 0 over 470, and that's equal to 0. And now let's put all the V1 terms together. So we'll have 1 over 330 plus 1 over 470 times V1 equals, and put all the other terms on the right. Well, these zeros, of course, disappear, but then minus 10 milli goes to the right and becomes plus 10 milli. It's 10 milliamps. We won't put the units here just to focus on the math. Okay, so then you calculate this, and that is 5.157 milli, and therefore V1 is the ratio. 10 milli over 5.157 milli, which is, to three significant figures, 1.94 volts, which is what we got with our previous analysis. Okay, our previous analysis was easier than this, but this is how to do it with the node voltage method. And as stated previously, for very complicated circuits, this is maybe our only way we can actually do a full solution of the circuit. Now let's look at a more complicated circuit. More complicated in that it has more essential nodes. Let's have a current source. Here we'll have a resistor. Another resistor going this way. Another resistor here. Coming down there. And then one going across like so. And let's say, again, this is a 10 milliamp current source. And we've got, here's 100 ohms, 220 ohms, 150 ohms, 470 ohms, and 330 ohms. Let's solve this circuit using node voltage method. All right, first step, identify all essential nodes where 3 or more devices are connected. And those usually end up being the places where we put the dots, because when you connect 2 devices, you don't need to put a dot because it's obvious that they're connected. But okay, so here we go. There are 4 of them, 4 essential nodes. Now we get to choose one to be our voltage reference. So let's choose this bottom one to be our voltage reference, and then that node has 0 volts as its voltage. For the remaining nodes, we need to label them with unknown voltages. So let's just go V1, V2, and V3. So we need to, at every node, write Kirchhoff's current law. So let's say over here at V1, let's see, there are 3 branches there. And so we can have, let's call this current, say, I1A, and this current I1B, and the current going up here, I1C. And therefore, at the node with voltage V1, Kirchhoff's current law would be I1A plus I1B plus I1C is equal to 0. And now we put in terms of either the sources or Ohm's law what those currents are, and we get our equation. Okay, I1A here, let's see, that would be current going down. Well, there's 10 milliamps going up, so I1A is minus 10 milliamps. Leave off the units. Plus I1B, let's see, so this is current through a resistor. So it's voltage drop V1 minus V2 in the direction of the current. So V1 minus V2 over the resistance, which is over 220. And then I1C going up here, let's see, this is the current through a resistor, and the voltage drop in the direction of the current flow is V1 minus V3. So this would be V1 minus V3 over 100 is equal to 0. Now, this 1 over a resistance, right, that's a conductance. Remember that conductance is the inverse of resistance. So we can either think of it as 1 over resistance or as a conductance. So we're going to rearrange this in the form G11 V1 plus G12 V2 plus G13 V3 is equal to some current I1, right? So this is a current, minus 10 milliamps. Voltage over resistance, or equivalently a voltage times a conductance, also has units of current. So all these terms have units of current, right? This comes with this equation right here. Sum of currents is equal to 0. And this will be our bookkeeping. And here, G11, everything that multiplies V1, well, that's 1 over 220 plus 1 over 100. G12, that's going to be the V2 term, and that's minus 1 over 220. And G13, that's what multiplies the V3, and that's minus 1 over 100. So we notice here, if you look at G11, so we're looking at this node, it's 1 over 220 plus 1 over 100. In general, GII is the sum conductances connected to that node, to node I. So we'd expect here at V2, we should get 1 over 220 plus 1 over 150 plus 1 over 470. At V3, we should get 1 over 150 plus 1 over 330 plus 1 over 100, and we'll see how that works out. Okay, and then what are going to be the off-diagonal terms in our matrix, because these Gij's are going to be the elements of a matrix. We'll have Gij, which is equal to Gji, is the negative of the conductance connecting nodes I and J. So let's see. G12 is minus 1 over 220. Here's node 1 and node 2. So the negative of the conductance between those two nodes is minus 1 over 220. G13 minus 100. Here's node 1 and node 3. So the resistance between those is 100, so the conductance is 1 over 100, and it's the negative of that conductance is what goes into the matrix. And then finally, I1 here would just be any source terms. Either can be from a current source like this, or later we'll see how a voltage source gives you a current term. All right. And now we just continue on and we go to the next node, node 2. So we look here and we could draw out a series of recurrents flowing out of that node. Let's call this I2A, I2B, and I2C. So then we would get at the node with voltage V2, I2A plus I2B plus I2C is equal to 0. That's KCL. Now we need to put in what those values are. And let's see. So I2A, that's the current flowing through a resistor 470 ohms from voltage V2 to 0. So that would be V2 over 470. I2B, that would be the current flowing from voltage V2 to V1 through a 220 ohm resistor. So that would be V2 minus V1 over 220. And then finally, I2C here, I2C, would be the current flowing through the 150 ohm resistor from node V2 to node V3. So voltage drop, V2 minus V3 over that resistance, which is 150. And those sum to 0. Now notice when we're writing these, since we're taking the currents to always flow out, that's going to be our convention. When we do voltage drops, it's always going to be the voltage at the node in question minus one of the other voltages. So in this case, the V2s all are positive, and the other voltages are all negative. So that's just the reality check there. And so we can rearrange that. Let's see. So for V1, we've got minus 1 over 220. And then for V2, we've got three terms, 1 over 470 plus 1 over 220 plus 1 over 150. That's times V2. And for V3, we just got this one term, minus 1 over 150. And there are no constants, so nothing to go on the right side. Again, we'll call this G21. This will be G22. And this will be G23. And this will be I2, which is equal to 0. Okay, so that's our second equation. Now we do a third equation at node 3, node V3. So we're going to have, let's call this I3A. This I3B, and that I3C. So let's write that equation. This will be now at V3. What are we going to get? Okay, I3A. So that's the current through the 100 ohm resistor going from V3 to V1. So V3 minus V1 over 100. Would be that current. And then I3B, that's from V3 to V2 through a 150 ohm resistor. So that would be V3 minus V2 over 150. And then I3C, that's V3 to 0 through a 330 ohm resistor. So that's just plus V3 minus 0. So just V3 over 330. And those have to sum to 0. All right, so we can see now our V1 term will be minus 1 over 100. That's V1. And V2, there'll just be a minus 1 over 150. And then V3 is going to have all these positive terms, 1 over 100 plus 1 over 150 plus 1 over 330. And that's got to be equal to 0. And we'll call that, and that should be times V3, sorry. So this will be G33, this will be G31, and this will be G32. Okay, so now we stack, and this would here would be I3, which would be 0. So the only non-zero right-hand side term is the I1, which is 10 milli. Okay. So now we stack everything into a matrix form, G11, G22, G33, G12, G13, G21, G23, G31, G32. And remember, because Gij is equal to Gji, it's a symmetric matrix. that would mean that the off-diagonal terms are equal. G12 is equal to G21, G13 is equal to G31, G32 is equal to G23. Okay, that times the unknowns, V1, V2, and V3, will be equal to the right-hand side currents, I1, I2, and I3. Now, for our particular system here, and we go through and plug these different expressions into a calculator, and I'm going to keep them as fractions so they're exact. This is what we get. 4 over 275 minus 1 over 220 minus 1 over 100. I'm going to need a little more space here. Minus 1 over 220, which is equal to this term. The G22 is 2069 over 155, 100. And minus 1 over 150 minus 1 over 100. This is equal to that. This should be equal to minus 1 over 150. And then finally the G33, which is this expression right there, it works out to be 13 over 660. Okay, times V1, V2, V3. And those are equal to what? The currents, the I1, 2, and 3. Well, the I1 is 10 milliamps. And I'll write 10 milli as, right, which is 10 1,000ths, as 1 over 100. And the other two we saw were 0. Okay, so we need to solve this in order to get our voltages. And so what we would do is either use a linear algebra solution tool in your calculator or on a computer, which in principle or effectively inverts this matrix and multiplies it times the right-hand side to get these voltages. And what we find, the three significant figures, is V1 is 2.64 volts, V2 is 1.89 volts, and V3 is 1.98 volts. Now with that, right, we know all the essential node voltages, and then we can calculate the currents through any of the resistors as difference of voltages over the resistance. We would know the voltage across this current source, so we could figure out the power it produces and so on. Okay, so we have solved the circuit at this point. So we can summarize everything we've done so far as a recipe. Let's just call this the node voltage recipe. Step 1. Identify all essential nodes. Step 2. Select a voltage reference, one of those essential nodes. Step 3. Denote unknown essential voltages as VI. I equals 1 to, say, N. On our previous circuit, N was equal to 3. That will be the number of unknowns and the number of equations. At each VI, write KCL in terms of VIs and the sources. 5. Solve the N by N system for the VI values. And at that point, you can use VI values, calculate currents, and etc., powers, and anything else you want to know. So that's our recipe. Now, one thing we want to talk a little bit more about is selecting the voltage reference. How are we going to select the voltage reference? Well, from what we've just seen, it's in principle arbitrary, but there might be some good choices. Now, so far we haven't looked at circuits with voltage sources, but we can see what would happen if you had a voltage source, and we'll do an example here coming up to show this. If this was a voltage source, if we used one of the terminals of the voltage source as our reference, well, then the other terminal is immediately known because we know that the voltage difference between those two terminals. And since one of them, those nodes, we know that one of the nodes is 0, the other one is just would have the value of whatever the voltage would be. So that can be a really good way to decide which of your essential nodes to use as your voltage reference. Okay, so let's call this 1. Use a node attached to a voltage source terminal. That's a good approach. And another thing that you could do independently or maybe in conjunction with this is use the node with the most devices attached. And why is that? Well, remember what happened up here when we went through and we wrote out these equations. We get, like for the GII term, we get a term in this that we have to sum up, one for every one of the devices that's attached at that node. So if we were to use the node that had the most devices attached as our reference, well, then we don't need to write a node equation there, and that is going to tend to mean that the other equations that we do write would generally be shorter. So that might be more convenient. Right? So these are just two important considerations when you go to decide which node to use as your reference. Let's now look at an example that has a voltage source. So here's a voltage source connected to a relatively simple circuit. There we go. This is 220 ohms. 310 ohms, 470 ohms, 100 ohms, and 3 volts for our source. Solve this circuit and use the node voltage method. Okay, step 1, find all the essential nodes. Here's 1 and here's 2. Those are all the places where 3 or more devices or components are connected. Step 2, choose one to be our reference. Well, let's see. This one is not connected to a terminal of a voltage source, and this one is. So this would be probably our best bet. These both have 3 devices connected, so on that, by that term, they'd both kind of be equal weighting. But this one's connected to the terminal of a voltage source. And that means immediately, let's call this voltage here V alpha, is equal to 3 volts. We know that voltage, because this is 0, and you go up 3 volts, and that's what you get. Let's call this voltage V beta. Okay, these are both non-essential nodes. And then our remaining essential node, let's call that V1. Now, we only have one unknown node voltage, and so we are only going to have one equation. All right, that's going to consist of summing all the currents flowing out here. Let's call this IA, IB, and IC. Again, we take them all flowing out. And then what's this current? Well, see, V1 on the right and 3 volts on the left. So that'll be a voltage drop of V1 minus 3 through a resistance of 220 ohms. That's that current, IA. IB from V1 to 0, our reference, remember, is at 0 volts. So V1 minus 0, or just V1, over 470 ohms. And then IC, well, it looks like it would be V1 minus V beta, which we don't know, over 310. But in this case, all right, this is a trivial node. This current IC must also flow down through the 100 ohm resistor. So those two resistors are just in series, and we can write this equation for IC as V1 minus 0 over this series combination. So that'll just be V1 over 310 plus 100. And those have to sum to 0. So now let's collect all the V1 terms. So we'll have 1 over 120, 1 over 470, 1 over 410. So 1 over 220 plus 1 over 470 plus 1 over 410 times V1 is equal to, the constant term is the minus 3 over 220. Put it to the other side, it becomes plus 3 over 220. And then we solve, just V1 is 3 over 220 over this expression, and that is equal to, exactly, it's equal to 5781 over 3863, which to 3 significant figures is 1.50 volts. And we have solved the circuit. Now let's say we wanted to know this V beta voltage. Well, now we know this voltage, and this is 0, and then this is just 2 resistors in series, so it's just a voltage divider. So we could say that V beta would be equal to V1 times the voltage divider formula would be 100 over 100 plus 310. And we already know this voltage here. Okay. Let's do another example. Let's look at this circuit here. And we'll put our voltage source right here. And this is 6.8K. I'll leave off the ohms here just so you don't write too much here, it gets too crowded. This is common, you'll see on schematics. Often you leave off the units, they're understood. It makes it a little less crowded. And our voltage source will be 5 volts. We'll put the units on that. Okay, so what power is consumed by the 5.1 kilo ohm resistor? Okay, so in order to get that, we'd have to know the current through the resistor, and then I squared R would be the formula. So we need to solve this circuit. Okay, find all the essential nodes. Here's one. Here's another. Now, got to be careful here. These are not 2 different essential nodes because they're connected by a wire. Those are all one essential node. Everything connected by wires is part of the same electrical node. Now we're going to choose a voltage reference. Well, this node is connected to a terminal of a voltage source, so that probably is our best bet. So we'll take that one, and then that will be 0 volts. And then we'll call this unknown node voltage V1 and this V2. So we've got two unknown voltages. Very well. So let's go to V1. What will our equations be? Let's call this here IA, and this IB, and IC, and ID. So at this node, we've got the sum of these four currents has to be 0. They're all flowing out. And now let's write those. IA would be V1 minus V2 over 2K. IB would be V1 minus V2. And here we have this situation with two resistors in series. And so this will be the same current flowing there. So we can just take the series combination and say this will be V1 minus V2 over the sum of these will be this current IB. So V1 minus V2 over 5.1K plus 3.3K. IC will be V1 minus 0 over 2.2K, so V1 over 2.2K. And ID will be V1 minus 0 over 1.5K, so V1 over 1.5K, and those sum to 0. So notice there are no constant terms in there. So a solution of this would be V1 is equal to V2 is equal to 0. So the only place where the voltage source will come in is for the equation for node 2. Okay, so let's look at that. At node 2, let's see. So we would have this current. Let's call this current here ID. Let's see. We got D already. IE. Let's call it IE. Okay, so what are the sum of the currents flowing out there? Well, IE flows out, and IA flows in, so what flows out is minus IA, and here you got IB flowing in, so that would be minus IB flowing out. And what does that look like? Let's see, IE would be V2. What is this voltage? Well, because we chose the negative terminal of the voltage source as our reference, then we know immediately that up here we've got 5 volts. So we can say V2 minus 5 over 6.8K. Let's see, then here, minus IA, well, that we can write it directly as it's V2 minus V1 over 2K. Right? Which is just the negative of this term right here, V1 minus V2 over 2K. And then this current, well, V2 minus V1 over 5.1 plus 3.3K, which is just the negative of that term right there. So that's V2 minus V1 over 5.1K plus 3.3K, and that equals 0. So here's where the voltage source term comes in. All right, so now let's rewrite things. The first equation, we've got 1 over 2K plus 1 over, let's see, 5.1 plus 3.3 is 8.4. 8.4K plus 1 over 2.2K plus 1 over 1.5K times V1. And V2, we've got two terms here. So this is going to be minus 1 over 2K plus 1 over 5.1 plus 3.3, which is 8.4K times V2. And that's equal to 0. That's our first equation. And our second equation here, let's see the V1, we've got these two terms here, which is the same as this. minus 1 over 2k minus 1 over 8.4k. So minus 1 over 2k plus 1 over 8.4k times V1 plus, and for V2, let's see, we've got 1 over 6.8k (1 over 2k), and then 1 over 5.1 plus 3.3, or 1 over 8.4k, and that's times V2, and that's equal to 0. So those are our two equations in two unknowns. And so if we just punch out all these numbers in a calculator, we get to four significant figures: 1740 micro, and they would be, this is a conductance, so it would be micro Siemens, minus 619.0 micro, and down here it's symmetric matrix, so minus 619.0 micro, and then the G22, this guy here, is 766.1 micro, and this will all be Siemens, but we don't put the units, times V1, V2 is equal to our source terms. Well, for the first equation, there were no constant terms, so it was B0. And for this equation, I'm sorry, for our first equation, that was up here. First equation, there was no constant terms. Our second equation has this minus 5 over 6.8k, which would go to the right and becomes plus 5 over 6.8k, and that is equal to, in decimals, 735.3 micro. So that's the system we need to solve. Now, your calculator may do linear equations, and on exams in this course, we won't ever do more than a 2x2 system, so that you're not spending too much time on the linear algebra. But let's say you had to solve this without having an actual linear algebra solver on your calculator. You could use Cramer's rule. And so we'll write Cramer's rule like this. This is symmetric matrix, so AB, BC will be the entries, times unknown x, y values will be equal to constants E and F. All right, and in the notes, we go through and we show that the solution to this is to define D be equal to AC minus B squared, which turns out to be the determinant of this 2x2 matrix, AC minus B squared. And then X is EC minus FB over D, and Y is AF minus BE over D. So that's something you can do in a calculator, especially if you have some memory registers where you can store these A, B, C, E, and F values, and then calculate the D value and store it, and then just recall those values and do this calculation. So if we did this for our current case, we would calculate that D would be AC minus B squared, so that would be 1740 micro times 766.1 micro minus the square of minus 619 micro, and of course when you square it, the minus sign goes away. And that value is, to four figures, 0.9499 micro. And then the X, which would be our V1, would be equal to EC, let's see, so E is 0, okay, so that would be 0, minus FB, so this is F, and this is B, so it's minus, so it's a plus. Or we can just write that explicitly, so minus, and then the B here is, well, let's see, actually we want to do the F first, doesn't matter the order, but still let's do it like it's written here. 735.3 micro times the B value, which is minus 619, there. Those two minus signs will cancel. And that's all over our D, which is 0.9499 micro. And punching those numbers, we get 0.4791 volts, the four figures. And then Y, which would be our V2, would be this expression. AF, so AF, that's non-zero, minus BE, and E is 0. So we're just going to get the AF term. This times that. So that's going to be 1740 micro times 735.3 micro over 0.9499 micro. And that is 1.347 volts. So we have solved this circuit for the voltages. Now with those voltages, we were originally asked, what is the power consumed by this resistor? So we need to get IB. And what is IB? Well, it's V1 minus V2 over 5.1 plus 3.3K. Okay, so IB is equal to this voltage, 0.4791, minus this voltage, 1.347, over 3.3 plus 5.1K, which we said is 8.4K. And that is minus 103.3 microamps. Okay, and so what is the power dissipated in the 5.1K resistor? It's I squared R. So 5 power is 5.1K times minus 103.3 micro squared. Punch those numbers and you get 54.4 microwatts would be our answer.